Hello, welcome everyone. So this is the second part of chapter 7, and we're going to dive a little bit deeper into electron dot structures, go into resonance structures, and talk about formal charge. Okay, I'm going to actually start out with isoelectronic structures and continue from there. Isoelectronic structures are structures that are bonded similarly. So what's going to be a really quick way for you to solve problems is to recognize that elements in the same column have the same outer electron configuration, the same number of valence electrons. That means they're going to bond in a similar fashion. So H2O, or water, shown here. The bonding is such that oxygen wants 2 bonds and has 2 lone pairs, and hydrogen will also want a bond each. Since sulfur and selenium are in the same column, they're going to bond with 2 hydrogens in the same manner. So since you know how water bonds, if you see oxygen switched out with another group 6 element, you could assume that it's going to bond in a similar way. This is a nice shortcut. We already went over simple structures using Lewis dot, and there are some compounds that cannot be built in a really simple fashion just by looking at them, meaning it's just not obvious, right? When you see them, it's not obvious how to make the bonds, how many lone pairs. So when you can't do it by the simple method, which we did last time, you're going to do it this way. The first thing you're going to do is add up all of the total valence electrons in the whole molecule. That comes from adding up each of the individual valence electrons for each atom. Just to remind you, the group number on the periodic table is the number of valence electrons for that atom in that group. So oxygen is in group 6, it'll have 6 valence electrons or 6 outer electrons. If you're given a cation or anion, charged molecules, if you have a cation, you'll subtract electrons based on the charge. If you have an anion, you'll add electrons to this total valence count. We're doing this because those are the only number of electrons, that exact number of total valence electrons, you can use to build your molecule. The next step is you put your least electronegative atom in the center. H is always terminal. And then we're going to go through, form bonds to each atom. And each time we form a bond, we subtract 2 electrons from the total. The reason is each bond is made up of 2 electrons, and we subtract it from the total to just keep track of how many electrons we have left to use. After that, we fulfill octet or a duet for hydrogen. So you make sure you have 8 electrons around an atom and 2 for hydrogen. Okay, here's where it gets a little trickier. Sometimes you build your molecule and you have extra electrons. What do you do with them? This will happen in a situation where you are dealing with an atom in period 3 or lower on the periodic table. These have expanded valence. There are available d orbitals to accommodate more than 8 electrons around them. So you can actually put those remaining electrons on the central atom. Here's our first example, IF5, iodine pentafluoride. Count up the total valence electrons. These are all halogens, so I have iodine and 5 fluorine, so I have 6 halogens. Each halogen is in group 7, so 7 valence electrons. 6 times 7 is 42. I have to use exactly 42 to build my molecule. There's no ion charge, so I don't need to add or subtract any. First, we're going to put iodine in the center, shown here. Then I'm going to make 5 bonds to fluorine. Each bond uses 2 electrons, so 2 times 5 is 10. I just used 10 electrons. I started out with 42. 42 minus 10 means I have 32 left. The next thing I'm going to do is use those electrons to fulfill octets for all of the atoms. So iodine already has its octet and beyond. So that means for each F, notice that I have a bond here. You could have drawn 2 electrons, but this bond means that fluorine feels or can count 2 electrons, even though it's sharing it with iodine. Iodine can also count those 2. So the fluorine already has 2, it needs 6 more. So we put those as 3 lone pairs, 2 each on each of the sides of fluorine. So each fluorine needs 6 more electrons to fulfill the octet. 2, 4, 6, 8. So I have 5 fluorines times 6. I just used 30. I used to have 32 the last time I checked, and so now I have 2 left. Now you're in a situation where all the octets are filled and you have extra electrons. When you're in that situation, put those extra electrons as a lone pair on the central atom. So this will only happen when you have an atom that can accommodate more than 8 electrons. So notice, don't separate the electrons. Unpaired electrons means you have a radical. So you could put the 2 electrons here. I just happened to put it on top. You could have put it off here or off to the left. That doesn't matter. Okay, another special case is where you've actually built your molecule and you have no more electrons to use. You've run out of valence electrons, but the octets are not all filled. In that case, you have to start considering multiple bonds, double or triple bond. So our example here is formic acid. I wrote it this way just because this is kind of how it's bonded, but sometimes it could be written CH2O2. But I'm going to tell you a little bit about the skeleton because this could be bonded in a variety of ways. I'm going to give you a hint. Carbon is bonded to 1 H and 2 O's. So carbon here is bonded to 1 H and 2 oxygens. That means that last hydrogen must be bonded to one of the O's. So I just put it on the lower one. Didn't matter, you could have put it on the upper one. So our first step is to count the total valence electrons. Each H gives 2, carbon's in group 4, so that gives 4. And then each oxygen is in group 6, so that gives 6 each. So we have a total of 18. I'm going to put the least electronegative in the center. Hydrogen's always at the end. And then I'm going to make my single bonds to the ones I specified. And then the OH bond as well. So that used 2, 4, 6, 8 electrons. I started out with 18. I just used 8, so now I have 10 left to build the rest of my molecule. And the next step is just to use those to fulfill octets. So what I do is focus on this left structure here. I put in lone pairs. And I focus on the outer atoms first. So oxygen had 1 bond, so it needed 2, 4, 6 to fulfill an octet. This lower oxygen already had 2 bonds, so it fell 2 with carbon and 2 with hydrogen, so it already had 4, so it needed 4 more. So 2 lone pairs will give 4. So that used up 2, 4, 6, 8, 10 electrons, which I had 10 already left over from last time. So 10 minus 10, I now have none left. But what's my problem with this structure? The O octets are filled, the H duets are filled, but the carbon octet is not filled. So in this case, you can't just magically come up with some electron to just put on carbon. That's not allowed. So you have to share with a nearby atom, such as this upper O. This upper oxygen has this lone pair that can actually be used, those 2 electrons can be used to form a second bond. The beauty of that is that it shares those electrons. So oxygen still feels that it has those 2 electrons to count in its octet, but now carbon can add those 2. So now carbon will feel, and I drew the new structure here. Notice I use an arrow to show that those electrons are moving here to form the second bond in the carbon oxygen bond. And so now carbon feels 2, 4, 6, 8. Now all the octets are filled. I used the correct number of valence electrons. The one thing I want to point out is you could have also used the lone pair on the lower oxygen and had an arrow going just to show that you'll form another bond here, and you would get this structure. That's also a valid Lewis dot structure. The reason is all the octets are filled, and you used a correct number of electrons. But I'm going to tell you now, it's not the preferred one. The preferred structure to draw is this guy. And the reason is the way that oxygen normally bonds is 2 bonds and 2 lone pairs. It could be a double bond, or it could be 2 single bonds and 2 lone pairs. In this structure here, this oxygen has 1 bond and 3 lone pairs, or 3 bonds and 1 lone pair. So this is still a valid structure, but this is the preferred major one. Would rather have 2 bonds, 2 lone pairs. Okay, let's look at another structure. And I'm gonna just, if you wanna practice, you could try to do ozone. It's O3, so 3 oxygens, and you could try to build that structure. So you could pause and build that Lewis dot structure, and I'll just continue. Okay, so this is ozone, O3. If we get a Lewis dot or electron dot structure, we arrive at this, where oxygen has a double bond on the left and a single bond on the right. All the octets are filled. We used a correct number of valence electrons, which would have been 6 plus 6 plus 6, 18. Okay, the reason why I wanted to bring ozone up is because there are some interesting observations that scientists noted. So first, let me give you some background. An oxygen-oxygen single bond is 132 picometers. That's longer than an oxygen-oxygen double bond of 121 picometers, so shorter for the double bond. When they looked at ozone, they didn't find a single and a double bond length. They only found 1 bond length of 128 picometers. So I want you to pause this and just have a think about why that is. Why don't you find 121 sometimes, 132 sometimes, but instead only find one that's measuring 128? So the reason is these aren't 2 separate structures that exist. And I'm sorry, I just kind of jumped the gun a little. This is a structure that we just drew for ozone. And we showed the double bond on the left side, but there's equal probability of us drawing, or maybe not equal probability, but you could also draw the double bond on the right side and a single bond on the left. These are 3 different types of oxygens. So again, you could have the double bond here. Some of you may have drawn the double bond on the right. So you could draw 2 different structures. We call these resonance structures. The thing is, though, these actually don't exist. And I know that's a little hard to understand because I just drew it and they're valid Lewis dot structures. But remember the data that I just showed. We never see a single and a double bond. We never see one or the other. What we see is something in between. So in reality, what's happening is, as chemists, we like to draw these really finite structures to get a good picture of something. But in reality, there is only 1 molecule and it exists as a blend. It doesn't have single and double bonds. It's a blend of 1.5 bonds for those OO bonds. Okay, so what I want to tell you is that these are called resonance structures or resonance forms. And the electron here is spread throughout the molecule. So you can see it a little better here with this dashed line. And the overall molecule has this character. We call this the resonance hybrid, and it's a hybrid of all the resonance structures you could draw. Okay, so let me give you an analogy. You have a blue horse and a red donkey. Those are the resonance structures. We show a double-headed arrow in between them. Here's your blue horse, and on the right you have your red donkey. These are 2 different resonance structures, but the actual molecule is neither of those. It's a blend of those. It's a resonance hybrid, a purple mule. Yes. Okay, so the resonance, the molecule that exists is a blend, and it mostly resembles the lowest energy or most stable one. These are actually identical in energy. So that's why we have 1.5 bonds here. Let me just really lay out to you what resonance structures are. First of all, resonance structures, if you just look at them, they basically show electron movement with a molecule. So those, we just draw it as lines, but you have to think in your head that those lines, those bonds, those have electrons, and certain electrons can move throughout a molecule. The basic framework of a molecule will stay the same. It's only if you have a double or triple bond or lone pairs, those can spread out through a molecule, depending on the type of atom connectivity you have. These are not real. Resonance structures are not real. They're not detectable because they don't exist. They're just a picture for us. They're a conceptual tool for us to understand the polarity of a molecule and the reactivity. When you guys, some of you are going to go on to organic chemistry, you guys will look at resonance structures a lot to explain reactivity and products that you get. And a molecule should be thought of as the weighted average of all resonance structures, mostly resembling the more stable structure you could draw. And I'll go into how you decide that. How do you know which structure is better, meaning which one's lower in energy and hence a major contributor to the overall structure or overall hybrid? So we look at something called formal charge. This is a charge given to an atom when it doesn't bond normally. So remember when I said oxygen normally bonds having 2 bonds and 2 lone pairs? In that case, there is no formal charge. The formal charge is 0. So if we look at formic acid here, oxygen has 2 bonds and 2 lone pairs, 2 bonds and 2 lone pairs. We end up getting formal charges of 0. I'll go into how we calculate that. But over on the right side, it doesn't have 2 bonds or 2 lone pairs, so they do get these formal charges, plus or minus, shown here. The way we calculate that is we take its group number. For oxygen, it's 6. And you subtract the number of non-bonding electrons. So these are these guys. So for example, let's look at this upper oxygen here. The group number is 6, minus the non-bonding electrons. So 1, 2, 3, 4. Minus 4. And then minus the number of bonds, 1, 2. Minus 2, so that's how we arrive at 0. So anytime you have oxygen with 2 bonds and 2 lone pairs, you'll always get a formal charge of 0. That's its happiest state. Anytime you are different than this normal type of bonding, you'll have a formal charge. So here, oxygen is group 6, minus 6 non-bonding electrons, minus 1 bond is minus 1. Excuse me. Down here, we're still looking at oxygen. It's group 6, minus 2 non-bonding electrons. So notice, these aren't, I'm not counting pairs, I'm counting the individual electrons. Minus 2, minus 1, 2, 3 bonds, I get plus 1. The overall sum of the charges should add up to the overall charge of the molecule. They should all add up to 0. How do I know which one's better? I look at the numbers. The one that has the smaller number, 0's better than 1's, 1's better than 2's, those are lower in energy. So right there, because you're deviating less from the normal, right there when you have 0's, that's preferred. You see plus 1's minus 1, not as good, but it's going to contribute a little. If you start seeing minus 2 plus 2, that's going to be pretty bad. And it's going to be a very, very minor contributor. The other thing, we don't have this situation, but if you can make a structure that has the negative charge on the more electronegative element versus a more positive one, that's better because it can handle that negative charge more. The other thing is, why did I just choose oxygen to do this analysis? What about the hydrogens or carbon? I only look at the atoms where bonding is changing. So here, carbon, it has 4 bonds. In this structure, it also has 4 bonds. Nothing changed. carbon's group 4. So 4 minus 0 minus 4, it ends up being 0. Here are some general rules. Sometimes people have difficulty drawing resonance structures or resonance forms. Keep the skeletal framework the same. Don't mess with the single bonds. Only electrons move. So electrons in the second bond of a double bond or the second or third bond of a triple bond, those move. And lone pairs can move. Every structure you draw should be a valid Lewis dot structure. Don't exceed the octet for second row elements. You're looking to complete octets. Keep track of lone pairs and formal charges, because that's how you figure out which one's lower in energy and which one is going to contribute more to that hybrid. We use double-headed arrows in between different resonance forms and brackets around the entire set. The overall charge of the molecule is same for each structure, and the low energy forms contribute most to the overall structure. Some tips, just to remind you, this is normal bonding for groups 4 through 7. Carbon with 4 bonds, nitrogen with 3 bonds, and it could be a double bond and a single bond or a triple bond, but still 3 bonds in a lone pair. Oxygen with 2 bonds and 2 lone pairs, and halogens with 1 bond. And again, if this applies to oxygen, it applies to all the other elements in group 6. Any other type of bonding for those group members, then you're going to see a formal charge, and you should be able to calculate that. The farther from the normal bonding, the higher the formal charge. So let's look at our example. Oxygen here on the right has either 1 bond or 3 bonds. So right there, we know it cannot have a formal charge of 0. And then you could go ahead and calculate it. Here, just like we did on the previous slide, 2 bonds, 2 lone pairs, bam, I already know it's 0. So let's just practice. Take a look at these resonance structures of carbon dioxide. Just by looking at it, can you tell what is the major contributor? Meaning which one is the lower energy one that contributes most to the overall resonance hybrid? Does one look better than the others to you? And then go ahead and calculate formal charges. So pause this and take some time to do that. And the center structure is the major contributor because all the formal charges are 0. Here, this was an easy one because I already told you, with 3 bonds or 1 bond isn't as good. But be able to calculate formal charges for anything like a nitrogen or sulfur in a variety of different molecules, and you'll have practice on your homework for that. Okay, so that's where I'm going to end it here. We're going to do more with geometry. So we've already put into place a lot of how to build structures, and that's only in 2 dimensions. So now we get to go into something a little more interesting, looking at molecules in 3D. And this is important because there are some geometries that molecules adopt that will allow for reacting or prevent chemical reactions from occurring.